Yes. Okay, now it's on. Thanks the organizer for inviting me and for organizing this great event. I've enjoyed all the talks so far. I should warn, well, anybody who was in Regensburg last week, I gave a very much the same talk. So in that case, you're excused and may sample the meatballs upstairs and report back for lunch. So the title of the talk is Quantization commutes with reduction in 2 dimensions. I think when I was discussing this as a conjecture, so this is a recently proved part of the story has been recently proved jointly with my collaborator Dan Pomerleano, collaborator and former student, I say, a long time ago. When I gave versions of this talk at the conjectural stage before, I called it the quantum GIT conjecture. We'll see why. And I should say it's the category level of the talk will be very low. It's going to be about vector spaces at the end of the day. But the origin of the statement comes from higher categories, namely three-dimensional topological gauge theory for compact Lie groups, not for finite groups. So I point out that some other mathematics has developed now the point where in some areas we can brag to be slightly ahead of some physicists. It's the wrong audience to make this pitch, I know, but so techniques that were developed from mirror symmetry initially, now we know how to generalize to higher dimensions, and some statements now make sense and give complete pictures, mathematical rigorous picture for what happens, at least in dimension 3. Dimension 4, I personally don't know about. I mean, I'd love to understand gauge theory in dimension 4, but I don't. But in dimension 3, I think there's a fairly good understanding now, and I think this, what I'll describe now, was always for me the motivating application, and it was one thing. Lacking a proof of it was one thing that kept me from writing what I thought was a good account of the story. All the other applications were just reformulation, nice reformulations of known things. But this is a new result. It generalizes all the work from the 1990s from mirror symmetry for toric varieties, work of Batirev. It includes numerous other things, but I think the best approach, which I think I realized later, is the best motivation for it is to start up in even lower dimension. So I'll discuss quantization commute reduction in 1 dimension first, remind you of that, which is very classical material, maybe even semi-classical material. Classical. A review of 1D. Semi-classical story. What's the datum in the semi-classical case? Have a symplectic manifold. The phase space of a physical system. G is a compact, let's take it to be a compact Lie group. And acting on X. And we always require in this setting that the action be Hamiltonian. Means that there's a moment map from X, the dual of the Lie algebra, so that contracting with vectors in the Lie algebra give you the Hamiltonians for the infinitesimal group action. So I guess mu contracted with psi is a Hamiltonian for the vector field for the derivative by action by psi. In the quantum story is now quantum mechanics in this case. Mechanics, I can't spell this anymore. And you have a Hilbert space of states. And the analog of this is, of course, a representation of G on H. Okay, what do we do with this? Actually, I need both. you can construct the reduced space. You want mod out by the G symmetries. I'm not sure if we would call this condensation nowadays, but back in the day, it was just called reduction. You don't, in the semi-classical side, you don't just divide by G because that wouldn't give you a phase space, it wouldn't give you a symplectic manifold. You do what's called a symplectic reduction. X mod G, and that's by definition is zero in the inverse image of zero under the moment map divided by G. If it's smooth, then it's a symplectic manifold. Symplectic if smooth. On the quantum side, we think that modding out by symmetries, well, maybe not modding out, is taking the invariant subspace. So it's the quantum reduction. Well, there's a procedure that takes us from left to right. It's called geometric quantization. It needs a little bit more data. Geometric. You need a line bundle on X with connection. Yeah, L is now a line bundle. The connection should have curvature, a symplectic form. And in the polarization on X. And then the H you build out of that are the sections of L. L2 may be sections of a line bundle, which are invariant of the polarization. So A is L2 of X with coefficients in L, invariant under P. I'm not sure how to put that here. And if this data is also G invariant, then of course you get a space with G action. So an example that's a motivating example, it's not the example we'll talk about, so maybe I write here. The example is when X is a cotangent bundle of a space M, G acts on M, and then X mod G is going to be the cotangent bundle of the quotient space M mod G. Then there's an obvious vertical polarization. And being constant along that just tells you that the Hilbert space is just L2 of M with just that, L2 of M. Okay, so now we'd like to have something go well here, right? So we've started with H and this space, took G invariance. And here, on the other hand, we've reduced by G, so we can again produce H for M. So that was X mod G. And you want to compare that with H built from X, G invariant. And the first observation is there's always a map this way. Why is there always a map this way? Because you can restrict functions or sections on X to mu inverse of 0, and then of course G invariants are exactly sections coming from the quotient. So this is a restriction to. And in this cotangent case example, you see immediately the map is an isomorphism, in fact, saying that G invariant functions on M are the same as functions on the quotient. So the question is that always true for any polarization, and that's not always, but it's true in an important case, and that was the famous quantization commutative reduction theorem. That was Guillemin and Sternberg. In the 70s, I think. That if X is compact and the polarization is complex and positive, so Kähler, X omega P, let's call it, is compact Kähler, the map is an isomorphism. So in other words, holomorphic sections of X with values in L taken invariants become isomorphic to holomorphic section on the quotient with values in L, maybe mod G. Let's write it a bit incorrectly. And I'll make a slight remark. It was improved in many, because it was such a nice statement, was studied and improved in many ways. You care, for example, about super things, like you might want to ask what happens to higher cohomology, and the answer that also works also for H star of X. Well, the higher cohomologies also agree. You can get more ambitious, and that's relevant. That's why I'm mentioning that. You can get a bit more ambitious and ask, okay, how about what's special about the coefficients aligned bundle L? What if you start playing with the line bundle? So changing that a bit, and then the statement begins to break down. For vector bundles, general vector bundles H star of X with coefficients in E. And because, and that's what I want to introduce, there's a difference between the two sides because you see restricted to, where was it, to mu inverse of 0. There's a better way to explain that restriction because that would take you out of complex. So let's explain that a bit because that will come up. So mu inverse of 0 sees a part of holomorphic section, and you can say exactly what you're missing. So the function mu gives rise to, you need one more piece of data, namely a quadratic form on the Lie algebra. So the killing form, for example, if it's a semi-simple variant form of G, allows you to build from mu a function, norm of mu squared. Use that as a Morse function. The minimum stratum, of course, is mu inverse of 0, and actually, let's be precise, called a Morse bot function in this case, because the critical points are not isolated. The mu inverse of 0 is the minimum. That gives a stratification of X. There's an open, big open stratum, the thing that flow to the minimum. That's called the semi-stable part. So X semi-stable inside X is open. Lowest stratum. So this one flows, as I said, to the symplectic quotient, the quotient. And the fiber of flows to the minimum and projects to the quotient. The fiber over that can be identified with a complexified group. At least in the case when this quotient is free. So that's literally true if the G action on mu inverse of 0 is free. So from a complex point of view, I want to say restricting this open part and leaving out a lot of strata, complex strata. The stratification is holomorphic, can be proved. So this was studied by Francis Kirwan. So the statement, what happens when you have other coefficients? You have the invariant cohomology, H of X E, E contains, I put under quotes, the part you would have liked to see X mod mod G with coefficients in maybe E or C, plus what are called local cohomology on the other strata. I don't have to define local cohomology for you to make it plausible from here that yes, there could be some residual stuff. It's what you actually have, a spectral sequence, which converges to this guy, but contains this as a term. Sometimes it's useful to actually compute things. So the theorem in that setting is if you use the line bundle itself, then the other strata actually don't contribute at all. It's as if they were not there. The GS theorem that if E equals L, No contribution from other strata. Beyond X semistable. So that's a very old, very nice, I think, theorem in equivariant holomorphic geometry. So nowadays, after years of Muir symmetry, we would call this a B-model statement for quantum mechanics, because it involves holomorphic line bundles. And then you can ask, is there an A-model version? And the answer is yes, and it was worked out long before B-model and A-model words came along. It was worked out by Frances Kerr-One. Very nice little book. That was, I think, essentially her thesis. So what would A-model mean in this case? So on the B side, we look complex geometry, holomorphic bundles, holomorphic sections. The A-model side is supposed to be somehow soft up to homotopy, and the thing we know up to homotopy is ordinary cohomology, for example. So what the A-model version is, so the first attempt is to compare the cohomologies of X invariants, the cohomology of X mod G. But actually, that was a very misguided attempt, because when if G is a connected group and it acts on a space, it acts trivially on cohomology. So taking invariance in this way would do absolutely nothing. So it couldn't possibly have any relation. So that was not the right thing to do. The right thing to do is take equivariant cohomology. So I don't know how happy people are with equivariant cohomology, but when looking at, say, the Ram cohomology of X, we replace function with super function, differential forms a differential. So what acts now is not just G, but a super version of G. And you have to take fixed points and then a super group going with G. And when you do that, that's one way to arrive at equivariant cohomology. But even so there is a map again, because you can restrict the equivariant cohomology of mu inverse of 0, or the semi-stable part. And this is, in fact, maps isomorphically to, actually correct that. This is isomorphic to the quotient when the G action, again, is free on inverse of 0. But now, just as before, in this procedure, you have left out a large part of X. And while somehow in the previous case, we proved that the leftover part didn't matter, in this case, we're looking at topology. Obviously, you leave out part of a space, the topology will change. There's no way that map can be an isomorphism. The theorem is instead the best you could hope in light of these constraints. The theorem there says that equivariant cohomology of X is filtered, has a filtration by the stratification, by the Moore stratification. The top part of the filtration is the part you wanted to see, and then there are parts coming from the unstable strata. So, and then here, let's be precise, I'll put Q coefficient. And so top part, the quotient, I mean, the variant homology of, and the rest, the direct sum of the equivariant cohomology of the unstable, the other strata. It breaks up the cohomology. There's no differentials, also like the way you see in homological algebra. So it's the best thing you could hope. The space gets broken up. Cohomology of a space is as if the strata were being disconnected. The question so far? No. Okay. All right, so you can ask in preparation of what I'm going to explain, why did this B-model theorem work out more nicely and cleanly and better than the A-model theorem? After all, I mean, yes, you can both sides, the theorems on both sides, but surely it's easier to state this one. taking invariance gives an isomorphism, than to say, oh, there's a filtration which collapses a spectral sequence, blah, blah, blah. And I think one answer is that the representation theory of G on vector spaces is very clean and rigid. Have a semi-simple, have a decomposition into the semi-simple categories, a character calculus, breaking up the representation, for example, extracting the invariance by projector. Whereas representation theory of a supergroup going with G on chain complexes is not like that at all. It's very soft somehow. It's all concealed in differentials in homological algebra. Very different, it has a very different flavor. You can talk about it. We don't usually talk about it as a representation theory, but it does. You can do it in homological algebra, but there's no such thing as a orthogonality of characters or anything resembling that. That was a one-dimensional story. Any questions about this? I'll go to two-dimension. You can keep the title, I guess. Yes.
This formulation about commutation of quantization and reduction in one dimension, is it also possible to formulate it in terms of deformation quantization, so that on the quantum mechanics you have algebra of operators instead of Hilbert space?
You can. Yeah, that's correct. But I would say you could erase the right-hand side. There's a formulation here. You can ask about deformation quantization of X. And if G is compact, you can make it G equivariant. And there is a statement that the quantum BRST reduction of a deformation quantization of X does give a deformation quantization of the quotient. That's correct. And a very, very complicated way to prove that is to invoke a theorem again of Guillemin, and I think maybe Uribe, which tells you that you can get the deformation quantization by looking at the asymptotics, taking very large powers of a line bundle and looking at Toeplitz operators, acting on that, and asymptotically, that does give a deformation quantization of X, but that would be a very complicated way to prove what is a homological algebra statement. But yes, there is a formal deformation.
Thank you.
Statement. Yes.
I don't know if this will be relevant in the following, but what if the symplectic quotient is not smooth?
Then the quantum, the holomorphic statement still works, but you have to be careful cohomology of what, because the line bundle may not descend downstairs, but there is something downstairs. There's a rank one reflexive sheaf, I think, whose cohomology agrees with that of a line bundle. But it's very robust somehow. This other side doesn't work. When the G action is not at least has a positive dimensional stabilizer, then it's a big difference between the equivariant cohomology and the cohomology of the quotient space. So that is a bit less robust. There's a huge literature on that. There's people then discuss slight perturbations of the reduction, which are generically smooth or at least orbismooth, and then you still get nice statements, and you can compare the cohomology of a slight deformation with the cohomology on X itself, and so forth. So,
Thanks.
What is the supergroup that you mentioned on the G side?
It's G and the Lie algebra. So, as I said, the action of G on cohomology, G is connected, is trivial. The reason it's trivial is because it's trivialized at the level of the algebra generator. So there's an odd copy of the Lie algebra, which acts by interior product on forms that trivializes infinitesimal group action. And those are the super generators you have to act.
The Z2 grading comes from the differential.
Sorry?
Where does the Z2 grading for the
how do you compute the cohomology of X? Just the differential forms and the differential D. And now you have a action. If G acts, you have first of all the Lie derivative action of vector fields. So C is an element of the Lie algebra, so it acts this by derivations. And then you have Lie's formula. says that the derivative like psi is a commutator is inner. The commutator with the RAM operator with the contraction operator by the vector field psi. And this expresses the fact that the Lie derivative action gets trivialized, it's inner. So from that, you can build a Cartan model for equivariant cohomology, where you take differential forms on the odd Lie algebra, or on the Lie algebra as an odd copy added on, and that is differential forms on X, and so the symmetric algebra on G functions on the algebra on G star, invariants, and you form the Cartan differential it's called, which is the Cartan is original differential plus something we construct from the interior contraction, psi A times I of psi A, where psi A is a basis. And this complex equivariant cohomology. So you add the differential forms on the odd part of the group. Like so there is a it's very, very classically old style homological equivariant homological algebra. So, but it's important that comes up in 2 dimensions, but I won't talk about that as well, this formal trivialization of the group action. It's true in any dimensions. One more board to erase. Time check as well. On 2 dimensions also, there's an A model side and the B model side. They're looking to build 2 two-dimensional field theories based on X, on a Kähler manifold X. And there is the A model side. I'm going to look at topological sectors only. And there's a B model side. And as we know now in 2 dimensions, TQFTs are generated by categories or derived categories, as the case is here. The B model side, I think, is everything is pretty solidly in shape. What we're looking at is a derived category of coherent sheaves on X, generates 2D TQFT. We usually ask for X to be Calabi-Yau, but actually that's only necessary if you want the TQFT to be defined for oriented surfaces. In general, we don't be defined for frame surfaces. And if you have a group action on X, you can form the derived category of G equivariant sheaves. Sometimes we call the equivariant derived category. So it is actually the G fixed point category inside coherent sheaves. So this, but you could also describe it as a category of G equivariant sheaves, so category of G equivariant sheaves or vector bundles. Okay, so you can ask if, well, so you can ask, on the other hand, I mean, going to the reduction first, you can ask versus derived category of coherent sheaves on X mod mod G, you could ask, do these two define the same TQFT? Well, for that to be true, these categories would have to be equivalent. So, and again, for the reasons I explained earlier, it can clearly not be true because going between these two guys, you've thrown away some strata in X, coherent sheaves may be supported on strata somewhere far away, and all of that gets lost when passing from X mod mod G. So no hope of an isomorphism, an equivalence of categories, EQFTs. But there is an analog of the A model story in one dimension. There is the analog of filtration of a covariant derived category, of which the top part is the one coming from the quotient. It's called the semi-orthogonal decomposition. I have semi-orthogonal decomposition of d of x g, for which the top part d of x mod mod g. This has been studied for some time now, I think, because algebraic geometry techniques existed for a long time, so we know how to address these things. I don't know the subject well, there are additional combinatorial choices to be made to define that. So let's say well studied. But I mean, if I erased the key part, but what might or should surprise you at this point is that we do not get the simple, clean quantization commutative reduction statement. Get the statement which looks like the A model side in one dimension, the filtration. And the bigger surprise, if you haven't looked at that, is that it's the A model side which gives a clean, straight statement. Well, modulo things that are not yet known about Fukaya categories and Gromov-Witten theory. So the category here, I write expected, EQFT is generated by the Fukaya category of X, built from Lagrangians, with Holmes being rather complicated things, Fukaya category. It's a very soft thing. It looks like chain complexes in homological algebra. And then the question becomes the fixed points in the Fukaya category versus the Fukaya category of X mod mod G. I say expected is only proved in some cases. For example, toric varieties and more. Technology here in math technology lags a bit behind here. And just as in one-dimensional case, for the clean theorem to be true, there was a positivity condition necessary in the positive polarization. There's a positivity condition here too. So positivity is on the manifold is that X should be a symplectic manifold, should be like the geometry, they call it strictly monotone. In algebraic geometry, they call it Fano, but the examples that you all know are projective spaces, flag varieties. C1 is positive, C1 of Tx. It's positive in algebraic geometry. The condition here is that the class of the symplectic form should be a positive multiple of the first Chern class, lambda times C1. And then one usually takes lambda equals 1. Positivity condition. And I'll state this as a conjecture. I think we can prove it now, but conjecture. Category fixed point of the Fukaya category is equivalent to the Fukaya category of X mod mod G, and there's an additional condition if G acts freely on the inverse of 0 and the technical term, and you use Fano of Fano polarization. But the pre-quantum line bundle really is a anti-canonical bundle. Don't worry about it. And I think we can prove that. We didn't go for this because You know, even if you prove it, you don't quite prove that TQFTs generated by two sides are the same because there's some missing steps in Fukaya categories and the TQFTs. So instead, what we went for is the space of states. What's a space of states associated with the circle? Space of states for S1 is known as also the quantum cohomology of X, or also the Fleur used to be Fleur homology of X. Actually, is a better definition. So what you want, so additively, if X is compact, it's the same as the cohomology of X. So additively, cohomology of X, but that's quantum corrections. And what we would like to relate, want to express the quantum cohomology of the quotient in terms of the quantum cohomology of X, somehow including in some way G. So let me write the first thing and let's see if people are paying attention. Tell me what I did wrong. In the equivariant quantum cohomology of X, and the first naive conjecture would be that these two should be equal. What did I say here that's wrong? And people should know that even for a finite group. Space associated with a circle. Why could those two not be equal? TQFT reason. Right? Exactly. It's a circle, there are twisted sectors. The most there could be is a map somehow. That's not the conjecture. That's not the quantum GIT conjecture. But let me say morally what happens that brings in exactly that. So morally, and you can make this precise, the quantum cohomology of X or Fleur homology of X, you may have seen that construction is built from Morse theory on the loop space of X. Of course, the two-dimensional TQFT, so I mean, you want time to move inside the loops in X, map from the circle to X. Now, if G acts on X, it implies the loop group of G acts on the loops group, acts on loops in X. And that's what you should be gauging by, not G, but the loop group of G. So the conjecture is that this is isomorphic to the LG equivariant quantum cohomology of X. That's a conjecture you want to state. So G here is connected, so for that, otherwise the next step to explain. So I haven't stated yet because I haven't told you how this comes about. So let's restate it. Let's unpack that to make it look like exactly like what Michele said. Unpack this. So for a group G acting on some space, let S, definition of the equivariant cohomology is a cohomology of a total space of a bundle. This tells you that S can be made into a bundle over BG. So let's call it the classifying space of G cross with S over the group G. That's by definition. And this is a bundle, so this is a bundle, so EG crossover G with S maps to BG. Fiber is a space S built from the action. So what is B of LG? A little calculation. Topology tells you that it's the group manifold G quotiented out, I put the homotopy quotient, by the adjoint action of G. So this should be the cohomology, equivariant cohomology of a bundle over group manifold G with fiber, something like the Fleur homology of the twisted sector present. That's what you expect. And the theorem is that with the assumption I stated, this is true. So what I'll do at the very end, very quickly explain how you define that bundle and maybe very quickly what makes it work, because the idea actually shows a lot of parallels with what happens in the holomorphic case in one dimension. So I find that somewhat surprising. Go from 1, 2 dimensions, holomorphic and like differentiable or homotopical get interchanged for the story. So theorem is true. When it will be written, that's a different question. True. And the comment I'll make, I tried very hard for a long time to find the proof of this using algebraic geometry in the Kähler case, because after all, quantum cohomology, usually you say counts holomorphic curves, so it's an algebraic geometry thing. I don't know an algebraic geometry proof, and there's a Floer theory proof, and it's one place where you see in a really hard way that quantum cohomology is about symplectic geometry and not about holomorphic curves. So comment, no algebraic geometry proof known. Floer theory. All right, so what can I tell you about? I'll tell you how you build this bundle. So 2 things, the building a bundle over G with fiber H quantum cohomology. I should want for it Floer homology. HF star of X. Well, Floer theory is, as I said, is built from Morse theory on the loop space of X. The Morse function isn't quite, it's a circle valued function. Let's call it alpha from Lx to U1. Well, how do you write it? Well, if the symplectic form on X was exact, then alpha on a loop gamma would be integral over gamma of theta. The symplectic form is not exact, but if it has integral periods, the exponential of this is still defined. Defined if omega is integral. And the critical points, it's pretty easy to see, are the constant loops. And that's why, in effect, you get an additive identification of the cohomology of X at the end of the day. Now, the beauty of it, though, is you can deform it a bit. You can add Hamiltonians. I should have said for symplectomorphisms. Let's call them G from X to itself, in which case you use twisted loops instead of loops. So loops which start at the point X and then G of X. And from a Hamiltonian, of course, you can exponentiate a vector field to get a symplectomorphisms. And now the Floer complex, instead of being built from constant loops, is built from periodic orbits of a symplectomorphism of period 1, so of the Hamiltonian. So from periodic orbits of the Hamiltonian. In the compact case, you can show that adding this Hamiltonian perturbation doesn't change Floer homology. So it gives you a lot of freedom, which we need to compute the quantum cohomology. And the third thing I will say is that Hamiltonian isotopy between symplectomorphisms gives an canonical isomorphism in Floer homologies. In symplectomorphisms. Isotopy canonical iso of Floer homology. The one parameter path of vectormorphisms that are given by a parameter path of Hamiltonian. Now I've told you enough to define this guy, because this guy is a bundle over G, the fiber at the group element G in G. It's not the quantum cohomology of X, but it's canonically the Floer homology of X for the symplectomorphism G. And the fact that Hamiltonian isotopies give you isomorphism of functional cohomology tells you that if you perturb G a little bit, you can identify nearby cohomology. So this is actually a local system. That system, this step, that bundle. It makes sense to take cohomology with values. G did not have to be discrete for the twisted sector presentation to make sense. Makes sense for a D group. Okay, and now that is defined. Let me tell you one just very vague idea. Actually, maybe before I have any questions now. I'll give you. I'll tell you a vague idea now why the theorem is true, how you exploit this. And then I'll restate that guy algebraically and return to what works about the A model in 2 dimensions that didn't work in 1. Idea of proof, the very old geometric idea. So turn on the Hamiltonian. U squared, Morse function we had before, times a very large number k. This gets very large away from the zero set of the moment, zero fiber of the moment map. So what happens? You get lots of periodic orbits near inverse of 0. Build a quantum cohomology, Floer homology of X. Now from complex, which has a lot of information in mu inverse of 0, and the theorem is that the thing to check is that under this assumption, the positivity assumptions, that all of the equivariant cohomology of X gets extracted from the unstable part and brought near mu inverse of 0. Extracted from X minus the part that gets thrown away, or the part that gets thrown away, and to come near inverse of 0. And now what you have is you have this neighborhood of mu inverse of 0 mapping to X. The fiber looks a lot like the complex group. Well, it's a complex group, looks a lot like a cotangent bundle of G. And there's a little bit of technical juggling you need to do here. Now you can relate, because you have a map, you can now compare the equivariant cohomology. Equivariant cohomology of X, which is now completely captured in here, the quotient H star of X mod G. And actually, the argument is geometric, but I want to rewrite this algebraically to say there is an actual formula, not just a story. So let's say omega G part loops in G kills the space of orbits in the fiber, kills the space of orbits. It's actually obvious when G is a torus. When G is a torus, so in T star X with in T star sorry S1, the obvious quadratic Hamiltonian, you have S1 here, and you have periodic orbits at integer points, and omega S1 Z, and what it does exactly, if you raise the action, it moves you between orbits, so just collapse them to just the base X mod G. But let me write the formula. Formula for H star G of G with coefficients in, what was it? Floor homology, I wrote it is. HF star X. Well, so if you have a variety, let's say space M, and you have a local system, a flat bundle, for example, but a general local system over M, that's determined by the monodromy representation, equivalent to a representation of the base loop space of M. Let's say M is connected. And taking cohomology with coefficients, homology, actually maybe homologies. I like homology better. Homology. G is compact, so actually you can play with that. H star of M with coefficients in this E is equivalent to something you can say group theoretically. It's taking the derived co-invariance under the monodromy. It becomes H star of, or H star, yeah, group homology of omega M. In E, and that becomes E, the fiber at the point tensored with the homology of omega M with just a trivial representation, just a ground field, maybe Q or C. And for this to be true, this has to be left derived. I won't get that. So we have to use homological algebra. I'm almost done. I won't use 10 minutes, don't worry. Maybe I'll write it on this side where I wrote that space. All right, so using this, we can describe a local system from the action of omega G on the Floer homology here. That's part of the loop group. But residually, there's a G acting everywhere. So, result, you get an, so the local system is described by an action of homology of omega G, the G equivariant on the fiber at the identity, which is the equivariant quantum cohomology X. So this is, I write homologies, but you have to write complexes, so I have to derive. And then that cohomology, actually the homology going with that, let's write it this way, homology, coefficient in this local system of X, becomes isomorphic to the equivariant. I guess I have to put homology of X. What if I do this? For quantum com. Tensored over, that's the way to do it. It's equivariant homology of omega G with just the equivariant cohomology of a point. Again, left derived, so with complex vector spaces. That is the formula for the quantum cohomology of the JT coefficient. G in under assumptions. That's the algebraic formula. So this is an actual formula, of course. And now let me tell you why I think this is the A model is clean in 2 dimensions when it wasn't in 1 dimension. It's because we're thinking of this as a gauge theory, 2-dimensional gauge theory, and gauge theory is 2-dimensionally by the boundary of 3-dimensional gauge theory. And 3-dimensional gauge theory, logical, controlled by holomorphic Lagrangian geometry inside the Toda space. Toda space. Let's say G or G dual, usually people, Langlands dual. As an example, Toda space for a torus, the cotangent bundle of the dual torus. This Toda space, the ring of functions, turns out to be isomorphic to the equivariant homology of omega G. This is also known as a chiral ring for the Coulomb branch for pure 3D gauge theory. Chiral ring. That's a result of Bezukhov-Kavnikov. Finkelberg. Identification. I need one more drawing now. Toda space is a completely integrable system. So Toda projects to vector space the dual of the Lie algebra. Now I'm getting on it. The Lie algebra, original Lie algebra modulo the group, the adjoint orbits, or the maximal torus model Weil group, if you like. Projection. Now, inside this space, boundary conditions for 3D gauge theory correspond to some coherent sheets with Lagrangian support. And there is a particular distinguished one that's a unit section of the Toda system, corresponds to the Neumann boundary condition. And this tensor product, where is it going? Here? Computes the intersection of the equivariant quantum cohomology X with the Lagrangian corresponding to Neumann condition, and that computes a space for the gauge theory of X mod mod G. And I'm done.
How hard would it be to generalize this for the case when we have G invariant superpotential on X?
Superpotential, but
well, in the Foucault category, we would have instead Foucault category.
okay. So actually, you have to be careful when you. So this theorem is true for small quantum cohomology when you didn't add, say, even bulk deformations. You have bulk deformation, something is still true. I mean, obviously, you have an equivalence of categories as an equivalence of deformation theories, but then there will be a deformation class. Not compute that. So I think study that in general, maybe even without the monotone condition, and prove that when relating the categories by correspondence, you expect, in general, there will be a deformation class. How easy it is to compute, I don't know. So it stops being explicit very quickly. I have no angle how to match the two sides.
Okay, thanks.
Thanks. So I have a naive question. So on the A model side, if you now take the mirror of X, what is the B model statement for what you just showed?
I would say this is the mirror of X.
That's the mirror of X.
The mirror of X will be, if you really have a complex manifold, then you would say the mirror of X would have to be some kind of manifold mapping to the Toda space with this support. Or actually, that's not, I mean, a mirror isn't unique, so it's a bit hard to answer that. But the naive mirror that you use for simplest mirror that is best understood, which comes from torus action, when T acts on X and you have a mirror X check, what you expect right away is X check to come with a map, the dual torus. And in this case, I didn't say it quite, it's a map the dual torus. So X check would be something mapping to the dual torus here. It's a projection this way. And this would be some unraveling of the structure sheaf of X check defined by some superpotential. That's how it works out. So this the cotangent bundle somewhere here. Yeah, this cotangent bundle this cotangent bundle here is to allow for a superpotential. I'm going to write the graph of a differential of a superpotential inside the cotangent.
Ask another question? Okay. So on the B model side, you mentioned for the derived category of coherent sheaves with X mod mod G, that was kind of the top part of the semi-orthogonal decomposition.
Yeah.
What about the other parts?
The other parts come from the other strata, I think that's as usual. But to define,
But do they look like derived categories of?
they come from derived categories of other strata with some constraint. You have to put some constraints on the weights of the stabilizer on the sheaves. Define the semi-orthogonal decomposition. There seems to be some additional combinatorial data coming in. The answer is yes. You.
The answer to the question in chat, yes.